morning. Let us continue our discussion on MO diagram for other molecules. So far we have seen MO diagram for H2 and then helium 2 and then Li2 and then similar diagram you can draw for beryllium 2. So, let us see more about MO diagram for other molecules. It is important to remember that in molecular orbital theory that mixing of orbitals. Okay, so, you have one energy level, for example, you have 1s orbital of one atom and it is represented like that. You have 1s orbital of for another atom, okay, it has 1s orbital and these two energy levels, atom A, this atom B, its energy level is here and they have same almost similar energy atom, okay, 1s orbital on atom A, 1s orbital atom B have the similar energy, that is why they are able to interact and you will get two MO diagrams, the MO molecular orbital energy levels which are represented in this way. If how many number of electrons are here, for example, 2 are there, then they will go here, 2 will go here and then 2 more will go here. So, at the end you can count the number of electron at the molecular orbital. So, here is the middle one is the molecular orbitals. These two are the atomic orbitals, contributing atomic orbitals. The number of molecular orbitals is same as the number of atomic orbitals combined to give them. So, number of atomic orbital is 1, 2, number of molecular orbital is 1, 2 and number of electron also remains the same. So, 4 electrons are there, number of electron is 2 plus 2, 4 electrons. So, this is a atom for helium because it has 4 electrons are there. Says this in the same way, if you have energy levels, okay, so if you have 1s orbital, orbital they interact and give it molecular orbital of this diagram, and if you have 2s orbital after 1s you have 2s orbital and then you have like that and they also interact each other and then you will get MO diagram like that. Okay. So, for example, after helium you have a lithium Li2 and then you have beryllium. Let us see beryllium Be2 and then you have a 2 electron, here you have a 2 electron, both of them will go here and will go here. In addition, you have beryllium electronic configuration, you have to remember for one beryllium atom 1s2, 2s2, okay, 2s2. So, the number of electron is into 2. So, equal to 8 electrons are there. So, 4 electrons are gone here. So, another 2 more electron here, 2 more electron and then you have to fill up and then fill up here. So, number of electrons in Be2 is 8 electrons, 2 plus 2 plus 2 plus 2, 8 electrons and then the bond order is these two, this is a sigma orbital, this is sigma star orbital, again this is sigma orbital, this is sigma star orbital. To find out the bond order, these two are cancel each other and these two cancel each other. So, there is no bond between no bond in Be2. So, that means it does not exist, Be2 like helium it does not exist. Let us see other molecules. After beryllium you have boron. So, if you look at the boron MO diagram, as usual you can write, if you this is 1s orbital of the boron atom. So, let us see boron B2 electronic configuration is 1s2, 2s2, 2p1. Okay. So, 2 borons means 5 into 2. So, number of electron is 10 electrons are there. So, 1s orbital you draw here, another 1s orbital of the another boron atom, here is the boron atom, another boron, the middle is the B2. So, you have 2 electron here and then 2 electron here, they interact each other and you will get 2 MO diagrams which are connected in this way and then okay, this is 1s orbital. After that you have 2s orbital they interact and then you will get like that. Okay. After that you have 2p orbital. So, in 2p orbital there are two types of orbital, they can also form a sigma bond as well as pi bond. So, you have in which you have px, py and then pz. The pz is for is for forming sigma bond, these two for pi bonds. Two pi bonds can form using px py orbital. So, they interact each other and then you will have, because okay, interact to give one sigma bond and two pi bonds can form using 2p orbital. As we you have studied that sigma bond is higher in energy, so that will be in lower energy. Okay. So, then after that a pi bond comes because its energy is higher, because overlap is less. So, it is usually placed here. Then you have to draw like that and then draw like that, then for these two and these two, and then you have a anti bonding pi star orbital and then a sigma star orbital. So, this is a sigma orbital formed by 1s orbital, this is a sigma orbital formed by 1s orbital, this is a sigma orbital formed by 2s orbital, this is sigma star, this is sigma star orbital formed by 2s orbital. This one is the sigma orbital formed by 2p orbital, this one is the pi orbital, that is px and py orbitals are there. So, pi orbital formed by 2p orbitals. Okay. So, this is a pi star orbital formed by 2p orbital. This is a sigma star orbital formed by 2p z orbital. Okay. So, this is 2p z sigma orbital formed by 2p z orbital, sigma star orbital is formed by 2p z orbital. So, now if you fill up for boron, as we have seen before, now what we have drawn here is the mixing of 1s orbital with 1s orbital, 2s orbital with 2s orbital, 2p orbital with 2p orbitals. So, we mixed them and we drawn the energy levels accordingly. Okay. Now, you fill up the electrons, 10 electrons are there, 2 put here, 2 put here, because 2 also. Another one is the 2s2. So, there are 2 here, there are 2 here, both of them, okay, all 4 will go here. On top of that 2p orbital, there is 1 electron here, it can be here, it can be here. Then you have to put here, because it is this orbital lower energy. Now, if you look at that, now both electrons are in one orbital, that is sigma orbital. Now, that means the molecule is, okay, the molecule is a diamagnetic as of now. Actually, it is not diamagnetic. Experimentally, B2 is not diamagnetic. That means there is electrons are paired up. Diamagnetic means electrons are paired up. Paramagnetic means there is a presence of at least one electrons. So, B2 is not diamagnetic. Actually, experimentally B2 was found to be a paramagnetic molecule. Okay. B2 is a paramagnetic molecule. So, if you fill up the molecular orbital diagram using these energy levels, this type of energy level, you will end up with a wrong conclusion about the B2. Bond order, if you want to calculate bond order equal to number of bond electrons. So, these two cancel, and then about here there is a 2 electron in the bonding orbitals. So, there is no electron in the anti-bonding orbital. So, 2 divided by 2 equal to 1, bond order is 1, that is correct. But the nature of the molecule is not diamagnetic, it is a paramagnetic. Okay. Experimentally observed that it is a paramagnetic, B2 is a paramagnetic. Then that means the diagram which we drawn just now is incorrect. So, what is the energy level, correct energy level diagram? Even if you go, for example, okay, it failed to explain our experimentally observed phenomena. Okay. Experimentally what is observed is a paramagnetic, which is not supported by this theory. So, then let us look for the whether it is a case, same case for C2 molecule. For next molecule is after boron, you have a carbon C2 molecule, there the number of electron is 12 electrons are. So, 12 electron will go here. Okay. After filling up, these two energy levels are degenerate. Okay. So, these two energy levels are degenerate. That means they have equivalent in energy. Okay. So, when they are equivalent energy, 2 electron, the remaining 2 more electron for carbon C2, 2 more electrons are there. Okay. So, those 2 will go to these 2 orbitals. one by one, okay, according to Hund's rule of maximum multiplicity, and then you will end up with conclusion of paramagnetism. So, as per this diagram, you will see that you can predict that C2 is a paramagnetic. Actually, it is not paramagnetic, it is a diamagnetic molecule. Then that means this diagram is not a suitable diagram to explain the experimental observed properties of certain molecules, for example, at least B2 and C2. Then what is the correct diagram to explain the property? Okay. Before we draw what is the correct diagram, we have to understand, okay, the concept of mixing. Okay. So, mixing of orbitals. Mixing of orbital is possible as long as energy levels are similar and symmetry is same. Okay. For mixing of orbital, two conditions, primarily two conditions are required. Okay. Energies are similar and symmetry of the orbitals which are mixing should be the same. Symmetry is the same. Okay. As long as these two conditions are met, okay, mixing can take place. So, what we have drawn here is the mixing of 1s orbital with 1s orbital of another atom, 2s orbital of the of one atom with 2s orbital. So, because these two energy levels are similar or equal, so that is why mixing takes place between these 2s orbital and 2s orbital. Okay. Now, there is also if the energies are so big, but there is no mixing between 1s orbital and 2s orbital, because the energy levels, the energy difference between 1s orbital 2s orbital is very large. There is no mixing between 1s orbital 2s orbital. Okay. But if there is if they are closer in energy, there will be a mixing. That is what happening for elements on the left side. For L2, okay, or for lithium 2 N2 molecules, for lithium to N2 molecule, there is a significant mixing of 2s orbital with 2p orbitals. There is a mixing between 2s orbital and 2p orbital of one atom within one atom. As a result, when there is a mixing happen, and then when they interact each other, energy levels are reversed. So, how it can happen? Because actually the mixing depends on effective nuclear charge, that is represented by Z star, which is lower than the actual nuclear charge. So, this is called effective nuclear charge. Okay. So, that effective nuclear charge increases from left to right. Okay. So, when you go from lithium to fluoride, the effective nuclear charge, that is Z star, increases. When the nuclear charge increases, okay, that is nuclear charge means the power to attract electron towards itself. Okay, so that increases from lithium to fluoride. When it is increases, okay, the electron present in different orbitals are attracted towards nucleus in different ways. So, you have after nucleus, after the nucleus you have 1s orbital, and then you have 2s orbital, and then okay, so you have 2p orbitals, okay, after the nucleus. So, these electron present in these orbitals are attracted towards nucleus in different ways, or in different attracted in different extent. As a result, okay, so they are pulled towards each other. As a result, there is a mixing between 2s and 2p orbital for elements located on the left side. For example, Li2 N2. If you go to O2 to F2, okay, the nuclear charge is increased. So, so the mixing is less for here, because the gap between 2s, the 2s and 2p gap is large. Okay. So, no mixing for these elements, for these molecules or elements, there is no mixing of 2s 2p orbital. What is the reason? The energy gap is more. Why energy gap is more? Because nuclear charge is higher. When nuclear charge is higher, okay, 2s orbital is pulled more compared to 2p orbital. So, that means the gap is increased. When the gap is increased, energy difference is more, there is no mixing. That is what happening for the elements located on the right side. But that is not the case for the elements located on the left side, because there the nuclear charge is, okay, less. So, that means 2s and 2p orbitals are not attracted as much as, okay, is not attracted as much as attracted for elements of this type. So, so as a result there is a mixing for these elements. When there is a mixing, 2s orbital, 2p orbital mix, and then when they interact, energy levels are reversed. So, you can see that if you draw a diagram, I am going to draw only the 2s orbital. This is a 2s orbital. You have another 2s orbital of another atom. Okay. So, there is a energy level, they interact and then they form. Then you have a 2p orbital. You have a 2p orbital. You have a 2p orbital here, and then as usual, okay, there is a bond. Okay, there is a double bond, okay, pi bond. This is sigma orbital, this is pi orbital, and then on top of that you have a pi orbital and then sigma orbital. So, you draw a diagram here and you can show the interaction in this way, and then you can show like that, and you can show, because now, okay, there is a mixing between 2s and 2p orbital. Then this is sigma star, this is sigma, this is sigma star orbital, this is pi star orbital, okay, this is sigma star orbital. Okay. So, because the effective nuclear charge is less for elements located on the left side, there is a mixing between 2s and 2p orbital. So, let us see that this type of initially this type of energy levels are formed. So, because of mixing, this sigma orbital is mixes with the sigma orbital formed by 2p orbital. So, there is a mixing, okay, there is a mixing. Okay, mixing between molecular orbital formed by 2s orbital, sigma orbital, molecular orbital formed by 2s orbital, and the sigma orbital formed by 2p orbital, they mixes. So, as a result, the higher energy level, this one is increased energy, the lower energy level sigma orbital is decreased energy. When this is increased, this is decreased, the pi orbital remains as such. So, as a result, there is a reversal in the order of orbitals, molecular orbitals, that I can show you in this way. So, keep this energy level as such. Okay. So, you have 2 orbitals. So, draw the diagram corresponding to this one, 2p orbital, this is 2p orbital, accordingly you have a 2p orbital here, and then you have a, okay, so 1s orbital, sorry, 2s orbital here, you have a 2s orbital, 2s orbital. Now, because of mixing, this energy level, okay, this energy level, this sigma orbital formed by 2p orbital, okay, is mixes with sigma orbital formed by 2s orbital. Because it is located in higher in energy, it goes up, and this is lower in energy. So, there is a reversal. So, when this goes up, okay, so that is it goes here, okay, there is interaction here and interaction here, and then, okay, so this level can be decreased here, and there is a decrease, and then you have a sigma orbital formed here, and then after that you have a pi star orbital, after that you have a sigma star orbital. So, this is a sigma star orbital forming 2s orbital, and this mixing, after mixing, this is a result. This is sigma star orbital, this is pi orbital, this is sigma orbital, this is sigma pi star orbital, this is sigma star orbital. So, you can see here there is a reversal in the order of molecular orbitals. Here, when there is no mixing, sigma orbital is lower energy. When there is a mixing, sigma orbital is higher energy compared to the pi orbital. Okay. So, this sigma orbital is resulting from mixing of 2s orbital and 2p orbital. So, you have to show the diagram from 2s to here and here and then here and then here, you have to show. So, it is a sigma orbital formed by 2p orbital as well as 2s orbital. So, that means it has character of both 2s and 2p orbitals, and pi orbital energy level is not affected. Okay, because of this interaction, this orbital is increased energy, this orbital lowered in energy, giving this type of MO diagrams. Now, this is the energy level present in elements present in the left side, So, if you fill up this diagram, this type of diagram using number of electron present in boron atom, then you will end up with the correct diagram and supporting the experimentally observed property of that molecules. So, if you take a molecule, for example, B2, number of electron is 10, okay, 4 already consumed, for example. So, you have okay, let me show you in another diagram. So, you have 1s orbital of boron. So, let us see, construct a diagram for B2 again. So, this is a 1s orbital, they interact and then okay, energy level is formed, and then on top of that you have okay. So, you have 2s orbital, okay, and then they interact okay, because of mixing. Okay, so, you have lower energy pi orbital and then sigma orbital, the contributing orbitals are 2p orbital. Okay, so, the corresponding 2p orbital. So, this has here on top of that you have a pi orbital, on top of that you have a sigma star orbital, this is pi star orbital. So, this one is a sigma orbital formed by 2s orbital as well as 2p orbital. So, you have to show the diagram there, it is there. For B2, number of electron is 10, here 2 here. So, it is 2 here, 2 here, they cancel each other for bond order calculation purpose. Here there are 2 electrons, here there are 2 electrons. So, 2 gone here, 2 gone here. Now, okay, there is 1 electron, because electronic configuration boron is 1s2, 2s2, 2p1. So, number of electron, total number of electron is 10. So, there are 5 electron on each boron atom. So, here there is 1, here is 1. So, both of them there are 2 electrons are available and there are 2 degenerate orbitals are there. Then both electron will not go to the same orbital when there is another orbital available which is having equal energy, that is these 2 orbitals are called degenerate orbitals. Okay, so, equal in energy and you have number of electrons 2 only. So, both electron will not go into the same orbital. Okay, according to the Hund's rule of maximum multiplicity, electrons are occupied, if energy levels are equivalent, electron will go to each orbital one by one, they are occupied separately. So, 2 electron, 2 molecular orbital, so 2 molecular orbital, degenerate molecular orbital, 1 here and 1 here. Then, okay, now the bond order remains the same, okay, bond order is 1, but the molecule, nature of the molecule is changed, now it is a paramagnetic. So, because there are 2 unpaired electron, one here, this is a pi orbital formed by okay, this is the pi orbital formed by px and py orbitals. This is a sigma orbital formed by 2p sigma, okay, this is a 2pz orbital. So, okay, there are 2 electrons in these orbitals, the bond order is 1, the molecule is paramagnetic. Now, okay, now this diagram explains the experimentally observed property of the B2, that is paramagnetic. In the same way, you can fill up the diagram for B2, for C2. Here the number of electron is 12 electrons, number of electron is 12. Now, already we filled up in this diagram 10, then 2 more will go here. Okay. Now, when you fill up these 2, because this is higher in energy, this is higher in energy. So, these now it explains that the C2 is a diamagnetic. Okay, C2 is diamagnetic and the bond order here equal to, so bond order purpose, these 2 cancel each other, these 2 cancel each other, and then you have a bonding orbital. So, there are 4 electron, the anti-bonding orbital there is no. So, bond order is equal to number of electron present in the bonding orbitals, molecular orbital, that is 4 minus 0 divided by 2, okay, equal to 2. The bond order is 2 for C2. Now, this diagram explains the property, actual property of the C2, which is diamagnetic. So, this is a actual diagram should be used, correct diagram should be used for explaining the property of C2 or B2 molecules. Okay. Now, you can also fill up this energy level diagram for N2. Here number of electron is 14 electrons are there, 7 electron from each nitrogen atom. So, 2 more electron compared to this one. So, those 2 electron will go to here. Okay. Now, I am removing this because we are changing that, and now 14 electrons are there. Now, 14 electron you can count 2, 2, 2, 2. So, 8, okay, 10, 12, 14 electrons are there. Now, for N2 the bond order equal to number of electron present in the. So, these two cancel each other, you have 6 electron in the bonding molecular orbital. So, 6 minus 0 by electron in the anti-bonding molecular orbital divided by 2 equal to 3. So, there is a N2 N triple bond between 2 nitrogen atom, triple bonds present in between 2 nitrogen atom, and the molecule is diamagnetic. No problem here, where molecule is diamagnetic. You can explain that. Now, there is some this is the energy level diagram for elements from, this is a suitable energy level diagram for elements Li2 N2. Now, let us see the energy level diagram for O2, for O2. Okay. For as usual, you can start with 1s orbital, interact, 2 energy levels are formed, and then you have 2s orbital, 2s orbital, interact, and then energy level is formed, and then you have a pi, you have a sigma orbital, there is a sigma orbital, then pi orbital. So, you have a 2p orbital, you have a 2p orbital. So, a pi bond is formed, as well as pi star orbital also formed, and then this is a sigma star orbital. So, this is formed here in this way, and you can construct a molecule. Here is a O, here is a O, this is O2, here this is the O2. Now, electrons here is the 8 electrons are there, 8 electrons here, there is 8 electrons, in total 16 electrons, 2 here, 2 here, here and here, here and here. And now, here energy levels is the first orbital. When you come to here, this is a sigma orbital formed by 2p orbital, and this is a pi orbital formed by 2p orbital. Now, see here the sigma orbital is lower energy compared to pi orbital, because nuclear charge is more for O2. As a result, there is no mixing between 2s and 2p orbital. So, there is no mixing. When there is no mixing, sigma orbital is lower energy compared to pi orbital. So, you have to fill up the diagram according to this, fill up this diagram using the number of electrons. So, 18 electrons are, so you have to fill up here and here and here and here, and then 2 more electron will go to here. So, now these two energy levels, this is pi star orbital formed by 2p orbital, this is sigma star orbital formed by 2p orbital. So, number of electron is 16, 2 to 8, 8, 10, 12, 14, 16 electrons. Here when you put the 2 more electrons, because these two energy levels are degenerate orbitals, so these are molecular orbitals should be occupied one by one. So, you have 2 unpaired electrons. So, O2, 2 unpaired electrons, 2 unpaired electron, that means O2 is a paramagnetic. Yes, that is correct. O2 oxygen is paramagnetic nature. Now, here I want to point out that what is the status for as far as valence bond theory is concerned. According to valence bond theory, electrons would be paired up. When there are 2 bonds between 2 oxygen, there is a 2 bonds. That means the maximum number of electrons are paired up. So, valence bond theory predicted the oxygen molecule as a diamagnetic, because electrons are paired up. Valence bond theory, according to valence bond theory, O2 should be a diamagnetic, because the stress in valence bond theory is on pairing electrons. Wherever for bond formation, electrons should be paired up. You need two number of electrons for formation of one bond. That is a basic concepts of valence band theory. Okay. So, as per its principle, valence band theory predicted that it is a diamagnetic. So, it is not diamagnetic, it is actually it is a paramagnetic. So, this is the one of the failures of valence band theory to explain the actual molecule. That is why another theory, this theory, that is molecular orbital theory, was developed, which explain what is observed experimentally. So, valence band theory predicted O2 as a diamagnetic, okay, but actually it is a paramagnetic that can be explained only by MO diagram, molecular orbital diagram, because you have 2 electrons here, 2 unpaired electron, 1 electron in each pi star orbitals. That is why O2 is a paramagnetic. So, you in molecular orbital theory, you just calculate to find out the what is the bond order, you have to find out number of electron present in the bonding molecular orbital minus number of electron present in the anti-bonding divided by 2. So, what you need is, okay, according to molecular orbital theory, okay, 1 electron is sufficient, okay, enough, 1 electron is enough for bond formation. Okay. So, 1 electron is sufficient for bond formation, but in valence band theory you need to have 2 electron for bond formation, that is a major difference. So, this is a now another concept which I would like to introduce here is the what is HOMO and then what is LUMO. HOMO is the highest occupied, this means highest occupied molecular orbital. So, LUMO means lowest unoccupied molecular orbital. So, what is HOMO? LUMO. Here for oxygen molecule, highest occupied molecular orbital is pi star orbital. That is highest occupied molecular. What is LUMO? Lowest unoccupied molecular. Lowest unoccupied molecular orbital sigma star orbital. So, that is what that is how you can identify which is HOMO, which is LUMO. HOMO is the molecular orbital, okay, occupied, highest occupied molecular orbital. For O2 is pi star orbital, because this is the orbital occupied. So, on top of that you have a LUMO, which is the lowest unoccupied molecular. So, on top of this there are some more orbital, on top of this there are some more orbital which are not shown here. So, this is the first unoccupied molecular orbital, that is called lowest unoccupied molecular orbital. Highest occupied molecular orbital is this one, lowest unoccupied molecular orbital is this one, that is LUMO. So, this is a LUMO, this is a HOMO for O2. See, it changes, as that you can find out based on the occupancy of the orbital, you can find out for every molecule which is LUMO, which is HOMO. Now, so you have molecular orbitals. Now, suppose this is a energy level diagram for O2. Now, the same way you can fill up molecules such as F2. Okay, number of electron is A. Okay, it's 18 electrons are there, because 9 electron from each fluorine atom. So, both remaining 2 more electron will go to these 2. So, the bond order is now will change to 1, because the bond order number of electron changes in the number of anti-bonding electron is changed. So, bond order is 1. So, similarly you can fill up for Ne2, so that 2 more electron will go to this one, and there is no bond between 2 neon atoms, and that molecule does not exist. Now, suppose, okay, so this is energy level diagram. It is, you know that okay, there are species O2, 2 minus, O2 minus and O2 plus. Here 2 electrons are added, because you take a O2 plus 2 electron you give, then you will have O2 2 minus, it is a peroxide ion. And similarly, and then if you look at the bond length and bond order, here for O2 the bond okay, the bond order is 2, the bond length is equal to 121 picometer, okay, and then 2 more electrons are given to the O2, and then it is found that the bond order is, okay, here the bond order is 1, okay, and then bond length is 149 picometer. Okay. So, 2 minus means 2 electrons, 2 minus equal to 2 electrons. Where do they go? So, when this is a O2 molecule, you give 2 electron to O2, those 2 electrons will go to, okay, the orbital, molecular orbital, okay, which is not occupied. So, if you look at these orbital which are singly occupied, that means there is a space. So, both electron will go to this pi star orbital. When electrons are added to the pi star orbital, it is going to affect the bond order. So, the bond order when you draw calculate for O2 2 minus, I am drawing only the outermost electronic configuration, molecular orbital configuration. So, you have a 2p orbital, 2p orbital, then you have a sigma orbital, then you have pi orbital, sigma orbital. Okay. O2 means here 2 more electrons, this is O2 2 minus, the number of electrons is 18 electrons are there, okay, because in O2 number of electrons is 16. So, in O2 2 minus means 2 electrons. So, 16 plus 2 equal to 18 electrons, that has, okay, that will go here in this way filled up, and then here and here. So, filled up. Now, if you calculate the bond order for O2 equal to number of electron present in the bonding molecular orbital, it is 6. Okay, number of electron present in the anti-bonding orbital, this is pi star orbital, this is pi orbital, this sigma orbital, this is sigma star orbital. So, 6, okay, number of electron present in the bonding molecular orbital minus anti-bonding electron 4 divided by 2. Okay. So, you will have, okay, so 1, the bond order is 1, 2 by 2 equal to 1. So, that is why I written here, when you give 2 electron to O2, it becomes O2 2 minus, okay, the bond order is 1, the bond length is 149, whether it is lower, higher compared to the starting O2, when you compare the bond distance found in the O2, it is 121 picometer only. Now, after giving 2 electron, the bond length is increased to 149. What is the reason? Because electrons are added to the antibonding orbital. Whenever electrons are added to the antibonding orbital, bond length, okay, bond order decreases. Bond order decreases. When the bond order decreases, bond length increases. Length is increased. So, as you can see here bond order is 2, bond order is 1. Okay. So, bond order, when bond order is higher, okay, its length is, okay, 121. Okay. And when bond order is increased or decreased to 1, bond length is increased, that is 149. So, let us see if you have, okay, O2 minus superoxide. Now, one more electron will go to, if you consider for one O2 minus, you have to put only 1 electron, minus means 1 electron, that will go to, okay, here. So, you will have for O2 minus, the bond order equal to 6 minus number of electron present in the antibonding orbital is 3 divided by 2 equal to 3 by 2 equal to 1.5. Okay. So, the bond order in this case for O2 minus, bond order equal to 1.5, and the OO distance was found to be 126 picometer. Similarly, you can have, okay, O2 plus, that means, okay, electrons are removed from O2. Which electron will go away? The electron present in the highest energy levels. So, if you want to make a O2 molecule, O2 plus molecule, that means 1 electron is less compared to O2. So, that which electron will go away? It is this electrons will go, any one of these electrons, because they are degenerate, one of the electron will go away. Now, you can calculate the bond order, that is 6 minus 1, that is 5 by 2, that becomes bond order becomes 2.5. Okay, for O2, the bond order equal to, okay, 6 minus number of electron present in the antibonding orbital is 1 divided by 2, 5 by 2 equal to 2.5 is the bond order. Then OO distance equal to in O2 plus is 1 picometer. Now I am going to summarize them. Okay. Now, okay, so if I summarize them, the highest bond order is found for O2. Okay, so O2 plus has the highest bond order. Then you have your O2. Then you have so called O2 minus, and then you have O2 2 minus. Okay, the bond order, okay, is here it is 2.5, here it is 2, here it is 1.5, here it is 1 only. Then bond length, if you look at it, okay, it is 112, it is 121, 126, this is 149 picometer. So, you can observe relationship between the bond order and bond length. Okay. So, the bond order increases, bond, okay. So, then as it increases, okay, this decreases, bond length decreases. So, as it decreases, so increases. Okay. So, this increases. Okay. So, then it decreases. Okay. Bond length decreases. So, as the bond order increases, bond length decreases in this as shown by this way, and also you can see here O2 the bond order is, okay, 2. If you go to, okay, O2 2 minus bond order is 1, here it is 1.5, that is in between these two. So, that also you can see here the bond length is 149, here bond length 121. 1.5 is between 2 and 1. So, as similarly the bond length also between 121 and 149, that is 126, observed 126 picometer. So, you have to remember that when electrons are added, it will go to the highest orbitals, that is in case of O2 it will go to the antibonding orbital. When electrons are added to the antibonding orbital, bond order decreases. So, when electrons are removed from O2, it is the highest orbital electrons is removed. So, it becomes, so when the highest orbital in O2 is the pi star orbital, when electrons are removed from pi star orbital, okay, then the bond order increases. That is why in O2 plus the bond order is 2.5. When electrons are added to the antibonding orbital, bond order decreases. That is why in O2 2 minus the bond order is 1, bond length is longer. So, you have to remember plus means minus electrons, minus means addition of electron, plus means subtraction of electrons. So, you have to use two types of diagrams. So, if you want to use for atoms lithium Li2 N2, you have to use this type of diagram, 1s orbital, 1s orbital, and then you have a 2s orbital, this is a 2s orbital, this is 2s orbital. Okay, so, you have 2s orbital here, and then you have 1s and 2s orbital, and then you have 1s orbital, and then you have a pi orbital, and then there is a sigma orbital, then it is a 2p orbital. This is 2p orbital, and then that interact and that interact, and it is interact, and this is also you have to draw a line like that, and then there is a pi orbital, pi star orbital, there is a sigma star orbital here. Now, so this is a diagram should be used for molecules from Li2 to N2, as you can see here. Okay, so as usual there is a sigma star orbital, but pi orbital energy level is lower compared to sigma orbital, higher, this is higher in energy compared to pi orbital. For molecules from O2 to F2, you have to use this diagram. This is 2s, this is 2s. Then you have a sigma orbital, 2p orbital, 2p orbital, and then you have pi orbital. So, this is an molecular orbital diagram should be used for O2 to F2, for Li to N2, this is the energy level diagram. If you mix and use it, then you will not get the correct result, and then you will be predicting paramagnetic molecule as diamagnetic, and vice versa. Thank you.